You ever read a book and stumble across a character doing something that's really, really dumb? It's a throwaway line, maybe, a small action, but you know it's dumb. And then it bugs you for days afterwards. No? Just me then? Well, let me tell you about it anyway. I was reading Promise of Blood by Brian McClellan. And to start with, let me just say, I enjoyed the book. It was a great read. But in chapter 3, there's a scene that really bugs me. Nyla, a laundry maid, is disguising this kid called Jakob. And she takes ashes from the fireplace and then she mixes them with water in the palm of her hand and smears that alkaline mix straight onto the kid's face. Yeah, you're staring at me like I've gone crazy, but that kid should have had a burning face with potentially deep tissue damage. Ashes mixed with water creates lye, which is a very powerful alkaline substance that can penetrate deep into tissue and cause liquefative neurosis. It can melt your face off, especially with just a little bit of water as opposed to a lot. And I should know, I clean my hearth with ashes and water. And once or twice it's touched my skin, and even diluted as I use it, I know all about it. And this girl was a laundry maid. She uses lye to wash clothes all the time. I mean, come on! So, to stop you and me falling into the same trap, that's what I want to talk about today. Chemical facts you really need to know to build a fantasy world. Welcome to another episode of Just in Time Worldbuilding with your host, Marie Mullaney. We'll start by talking about that all-important pH scale that would have saved Mr. McClellan my ire. Okay, so this is the pH scale. It runs from 0, very acidic, to 14, very alkaline. In the middle, 7 is pure water, which essentially doesn't damage your skin at all. Now, here's the thing. We're used to thinking that acids will harm you. After all, Harvey Dent fell into acid, right? And D&D has an acid trap, not an alkaline trap. But actually, both sides can eat your face. Acids cook proteins into a hard scab through a process called coagulative necrosis, which can actually stop the acid from going deeper. Bases, or alkaline substances, liquefy fats through a process called liquefaction necrosis, turning the person into soap and sinking deeper until the substance hits bone. So an acid trap might leave a character scarred. A lye trap is much more likely to be fatal or require amputation. Some examples in your fantasy world of substances that can be dangerous. Lye, pH 12 to 13, created by leaching wood ash in water. It was commonly used for creating soap and was called potash water. Touching it can create deep skin damage. Next, quicklime or slaked lime, pH 12.4, which is produced by cooking limestone in a kiln. When added to water, quicklime undergoes a violent exothermic reaction, boiling the water and creating a highly caustic paste. It was historically used in construction as mortar and as a chemical weapon in naval battles to blind enemies. Here comes an icky one. Stale urine, pH 9 to 10. This was used extensively in tanning and dyeing. While less corrosive than lye, the ammonia buildup in large vats can irritate lungs and eyes, and prolonged skin exposure causes a very charming condition that they used to call tanner's rot. Now, onto acids. Look, you're not going to get lab-grade acids in a fantasy world, but mining and alchemy can give you some pretty harsh substances, like oil of vitriol with a pH of 0 to 1. This is an early sulfuric acid that was produced by medieval alchemists through the dry distillation of green vitriol, which is iron sulfide. Even a small alchemist vial could eat through cloth and cause instant painful burns. Then there's blue vitriol, which is a copper sulfate, pH 3 to 4. This is found naturally in some mining drainage. It is toxic and acidic enough to ruin crops or poison a town's water supply if a mine is located upstream. And lastly, there's good old vinegar, pH 2 to 3. It's a staple for preserving food and cleaning armor. Now, while generally safe, highly concentrated glacial acetic acid, which is attained through repeated freezing and distillation of vinegar, can be caustic. And as a bonus, here's some quick environmental hazards for you in the acid-alkaline sphere. The Ashkill Lake. After a massive forest fire, rain washes large amount of wood ash into nearby ponds. This can spike the water's pH to 10 or 12, killing all fish and making the water toxic to any traveler who tries to drink or bathe in it. Tanning districts. The concentrated waste from tanneries, a mix of high pH lime and acidic chromium-like salts, creates dead zones in city rivers where no life can survive, not even rats. And then there's cave drips. In limestone caves, moon milk or highly alkaline water can blind explorers if it drops into their eyes. Conversely, acid caves formed by sulfuric vapors can melt boots and lungs. So, don't make the mistake Mr. McClellan did. Look up your chemical substances and check if they're going to soapify your face or scar it. I still really enjoyed the book, so don't let the ashes in the water put you off. Go ahead and read it. And now, let's move on to endothermic versus exothermic reactions, and especially what they mean for magic. Okay, let's talk about magic, starting with frost magic. We've all seen the mage who snaps their fingers and a lake of ice freezes, creating a path to walk across. It's literally cool, as well as figuratively. But if you're building a hard magic system, you've got a massive problem right there with that spell. And that is thermodynamics. In chemistry, we have exothermic and endothermic reactions. Exothermic is like a campfire. It releases energy as heat. Endothermic is like an instant ice pack. It sucks energy from the surroundings to make a reaction happen. What does that have to do with this frost mage, you ask? Well, to turn liquid water into ice, they are performing a massive endothermic draw. They are sucking heat out of the air. So, if your mage freezes a lake, the air around the mage should theoretically become a blast furnace of discarded heat. Or, if they're drawing heat from their own body to power a fireball, they don't get frostbite. They get binder's chill, like in Rothfuss's books, where the internal temperature drops so fast they could die of hypothermia while standing in a desert. And I'll give Rothfuss this. Sympathy magic really understood thermodynamics in Name of the Wind. But thermodynamics isn't just for magic. If your magicless army needs to heat soup in the rain, they don't need a fire. They just need a sealed tin of quicklime and a splash of water. It's an exothermic beast that can boil water in seconds. Just, don't get it in your eyes as per the face melting section. Next up, let's talk about oxidation. Oxidation is basically just atoms losing electrons. When iron does it, we call it rust. When wood does it fast, we call it fire. In a lot of fantasy, mithril or orichalcum is always 10 times stronger than steel. But here's a thought for your world. What if magic metal isn't stronger? It's just noble. In chemistry, gold is a noble metal because it refuses to oxidize. You can leave it at the bottom of the ocean for 1,000 years and it'll come up shiny. Iron, on the other hand, will be a pile of orange dust in 50. A legendary sword doesn't need to be able to cut through stone. It just needs to be made of a metal that doesn't rust and is hard enough to be a sword. Imagine a world where every knight's armor is pitted, brown, and falling apart because they're fighting in a salt marsh. But the king walks out in a suit of god metal that looks brand new. It's not a magic shield, it's just superior anti-corrosive chemistry. So don't think so much about making an incredibly strong metal. Think instead about what oxidizes and what doesn't. And now we're returning to laundry to talk about saponification. Saponification is what happens when you mix a fat, like pig lard, with a strong base, like that wet ash lye we spoke about earlier. And that creates soap, which is cool. By the way, soap is one of the oldest chemical reactions in the world that we know about, that ash and water mix. So don't go pretending people don't know what soap is just because you're way back in the past. Their soap might not lather up the way ours does these days. That's a different chemical reaction, story for another day. But the lye soap, ashes and water did get people and stuff clean. However, not all soap is created equal. And that gives you a way to play with a class divide. The peasantry probably use brown soap, made from rendered beef or pig fat and wood ash. It's harsh, it smells like a barnyard, and it'll give you a rash if you don't rinse it off perfectly. On the other hand, the elite would have Castile soap. It uses olive oil and soda ash from burnt seaweed. It's white, it's mild, and it smells like actual flowers. Now, think of your rugged ranger character walking into a royal ball. He doesn't just look out of place. He smells like a tallow candle. You can't hide that with a fancy cloak. Chemistry is like the ultimate class snob when it comes to soap. Okay, now let's get on to a fun one. Solubility and what it means for assassins. Like dissolves like. This is the golden rule of solubility. Polar things, like water, dissolve polar things, like salt. Non-polar things, like oils, dissolve non-polar things, like wax, or some deadly toxins. If your assassin is trying to poison the duke, they better know their solvents. If the poison is an oil-based alkaloid and they drop it into the duke's wine, whoops, it's just going to float on top, like a big, purple, don't drink me oil slick. But if they put that same poison into the duke's butter, it dissolves perfectly, undetectably, best taken with toast. So, why is it called polarity and how do you determine it? Polar molecules have poles with partial positive and negative charges. A stream of polar liquid, like water, will visibly bend toward a statically charged object, like a rubbed amber rod or a comb. Non-polar liquids, like lamp oil, will not show this attraction because their charges are distributed evenly. But you don't want to test every liquid for polarity, so here's a quick rule of thumb. You can generally categorize materials by their source. Polar, water-soluble, includes salts and minerals, as in most earth salts, alum and vitriol, plant sugars and saps, like honey and fruit juices, and alcohols, like wine or spirits, though these are amphilic, meaning they can sometimes bridge the gap between polar and nonpolar. Nonpolar or fat-soluble substances include oils and fats, obviously, animal tallow, olive oil, and vegetable oils. Then waxes like beeswax or paraffin, and resins as in pine pitch or tree resins. And these do usually require alcohol or heat to dissolve, as they really don't like water. Before we talk about fermentation, give me one moment to tell you about Worldbuilding Blueprints. This is a world-building book I wrote which will take you from zero to hero in world building. And it's not just theory. It includes exercises and worksheets, like this one, which is part of the Day in a Life of chapter that will guide you to thinking about your character's sanitary habits, perhaps help you to avoid making some chemical mistakes. Digital copies of the color PDF and ebook, which is laid out for a phone or tablet, and the audiobook are all available on my website now. The physical book, which comes either in glorious cover as a hardback or significantly lighter and cheaper as a paperback, will be available by March 2026, once all the Kickstarter orders are fulfilled. Details to all that down below. Alrighty, enough of that. Let's talk about fermentation. Long before people knew what germs were, they knew about fermentation. They thought it was a vital force or a blessing from a god. But really, it's just yeast eating sugar and pooping out alcohol and CO2. Thing is, almost anything ferments. You can even ferment honey by adding water. Honey without water won't ferment because it's a supersaturated liquid. If you don't add water, honey is like gold. You can store it for 1,000 years and still eat it. Forget lembas. The best trail food in the world is honey. It's insta sugar energy and it never goes bad. Anyway, don't let me rabbit hole like that. Back to fermentation. As I mentioned in my food video, check out the information card if you missed that, you can even ferment foods in order to preserve them, like the Swedes and their surströmming, which is fermented herring. And fermentation isn't just for preservation and getting drunk. It's also a primary solvent for medicine. Most healing herbs aren't water soluble. They are in fact non-polar, as we just discussed. So you have to soak them in strong spirits to get the medicine part to be active. In addition, alcohol can clean wounds by killing bacteria as well. So honestly, a world without brewing is a world without effective medicine. No alcohol means no tinctures, no antiseptic for wounds, and no way to preserve herbal extracts. In fact, your healers guild should probably be the best brewers in town. Okay, and now let's talk about a really odd one, an off-the-wall bit of weird world building. Let's talk about prebiotic chemistry. Most fantasy assumes life needs the sun. But on Earth, we have life that has never seen the sun. It lives on hydrothermal vents. Instead of photosynthesis, turning light into food, these creatures use chemosynthesis, turning sulfur and heat into food. This is a very interesting life to examine from a science perspective. But from a fantasy or science fiction world-building perspective, this is pure, unadulterated gold if you want to go really wild. Imagine a whole ecosystem built from the ground up where the primary food source is not photosynthesizing plants, but chemosynthesizing tube worms. An entire civilization could arise around volcanic vents. Their crops could be bacterial mats that eat minerals, and the sapient species wouldn't smell like earth and pine. they'd smell like a matchstick factory. It would be an amazing twist on our normal sunlit worlds to create a dark world or an underground world where life works completely different. Chemistry isn't just for the lab. It's the physics of the small that keeps your world's logic from falling apart. Whether it's the smell of peasant soap or the heat of a major's frostbolt, the more you understand the reaction, the more real the world feels. So, next time you're writing a scene with fireplace ashes, maybe just use them for the garden. If you've enjoyed this video, drop a test tube in the comments. And while you're down there, hit the hype or thumbs up button, or both if you're feeling super generous. As always, a huge thank you to my channel members, especially the just-in-timers of the Stone tier: Jeff Hicks, Epic, Laura Bone79, A. Wellyard, Neil Buckley, Necromancer JM, Katie Kofi Mug, and Tony Lamanna, along with the Wood and Straw tier members. Your help allows me to keep making these videos, and I am very grateful. If you would like to support the channel, one free way to do that is simply to watch another video. And if you enjoyed this video, you will probably enjoy my video on the 9 geologic facts every world builder should know, which you can check out right now on screen, or you can follow whatever the algorithm is recommending to you from my back catalogue. And I will see you soon for another episode of Just in Time World Building.